So we're going to start with the next section 11.2, which is on power series. So to remind you again, as I had introduced in the previous section, the motivation and the idea of power series. So a power series is an infinite series of this form. So summation k going from 0 to infinity ck x raised to the power k. Now, if you take the sum till n terms, then it becomes a polynomial, and if you continue, it obviously is a series. More generally, one would have ck x minus a raised to the power k. So then your terms would look like this, and if you stop at n, then we have what we called the Taylor's polynomial. So if you go till here, then it's Taylor's polynomial. But if you continue, then it becomes a power series. Again, center of the series is A, and the coefficients ck are some constant. So after finding the Taylor's polynomial in the previous section, now we will see that the natural reason for why we have this form. So again, to repeat, if we take infinitely many terms of the Taylor's polynomial where we had stopped at n, we would get this particular form of power series, and power series is written as PS. Now there is a similarity with geometric series that we studied in chapter 10. So let's recall the geometric series. So a geometric series with the coefficient of a equals 1, the geometric series was a r raised to the power k. So if I put a as 1, then I would get the following series. And we know that this adds up to 1 over 1 minus r. This was a over 1 minus r. So it would be 1 over 1 minus r as long as absolute value of r is less than 1. So now what we're going to do is, instead of r, we are going to write x. And if we do that, we are going to get summation x to the power k, and you will get x's instead of r. And then obviously that is going to add up to 1 over 1 minus x. So instead of r, we have x. And absolute value of x is less than 1. So if you look at this series, clearly this is a power series where ci's are 1. So this C0, C1, all these guys are 1. And A is 0, which means the center is at x equals 0. So this is an example of a power series which adds up to a very nice expression, 1 over 1 minus x. Now we are going to use this similarity a little later in this section. The main important thing in this particular section is to understand the idea of convergence of power series. So that's the most important concept. So the idea is as follows. First thing to note is that power series is a series, obviously the word series. Hence, there is a concept of convergence. Remember, we spent some time studying series, for example, this series, whether it converges, like does it go to something or does it diverge. So we want to study the concept of convergence. Now this power series depends on x. That's why it's called power series. It's got x in it. Hence, whether the power series converges or not depends on what value x takes. To explain this even further, let's take an example. Suppose you choose x equals 1, any number x equals 1, and you substitute in power series that you have. then it is going to become a usual series. Like that usual series means a series which has just nothing but constants in it. And then suppose it converges. So you take your power series, you put x as 1, it becomes a series, and suppose it converges. Now, if you choose x as 5 or 10 or some other number, again, the same power series will become some other series. Obviously, if you put a different value of x, you're going to get a different series. And now it could happen that it may diverge. So the point here is that the convergence of a power series depends on the value of x. So if you have a different value of x, it could diverge. If it have different value, some other value of x, it could converge. So we are interested in finding those values of x for which the power series converges. So we are interested in those values of x for which the given power series converges. So this idea is put together nicely in this box. So first let's review a power series again. So a power series has a general form of this. We have seen this many times by now, where a and ck are real numbers and x is a variable. Ck's are the coefficients of the power series and a is the center of the power series. The set of values of x for which this series converges is called the interval of convergence. And the radius of convergence of the power series, which is denoted by r, is the distance from the center of the series to the boundary of the interval of convergence. So what it said is the following. So let's look at this diagram here. So these are the values that x takes. Now, for x values between here to here, a is the center, we have convergence. So that means if you choose any value of x in this interval, the power series will converge. If you are out of this interval, the power series will diverge. So this is called the interval of convergence, and the center is always a, and therefore this is the concept of radius. So this is the radius r that we are interested in finding. So therefore our aim is to find the radius of convergence and the interval of convergence that goes with it. First thing to note is the power series, any power series that you have, always converges when x is equal to a, because look at a power series, any of them. If you put x equals a, if you put x, take the value x equals a, then obviously this term is 0, so all that you have is 0 plus 0 plus 0, which adds up to 0, so it converges. So the power series always converges when x equals a, because the value of the series is simply 0. But of course we are interested in so suppose this is a, we are interested in finding this interval of convergence. So we will use either the ratio test or the root test, but root test is used rarely, that we learned in chapter 10. We can also use the result of geometric series, and you will see that in the examples, how to use it to find the radius of convergence and the interval of convergence. So there are three ways that a power series can converge. So this theorem tells you that there are three ways that it can happen. So let's look at them one by one. So the first way, it says the series converges absolutely for all x. So what that means is, so this is my center of convergence. You can choose a whatever you like, and if you want you can say okay, it's 1. Then if the series converges for all x, that means your interval obviously is minus infinity to infinity, because for all x, all these values, it converges. And if the interval is this, then the radius, so what's the distance from here to infinity, is infinity. So this is one possibility, and that's what he's talking about here. Second possibility is that you have a, and then you find an interval like this. So the distance from the center a is r. That means your interval of convergence is a minus r all the way till a plus r. So from here to here we have convergence, and in that case your radius of convergence is r, whatever this distance is to this point. So that's what he's explaining here. And the third possibility is that the series converges only at a. So that means your interval of convergence is just one value a, and that is always so anyway, as we agreed earlier on, that every power series will always converge if your x takes the value a. But if that is what your interval of convergence is, then the radius is obviously 0. The distance is just 0 because that's the only place where it converges. So that's what he's explaining in number 3. So to find this, there are two steps. We are going to use the ratio or the root test, and sometimes similarity with the geometric series, to find the interval of convergence and obviously the radius of convergence. And once we do that, then we confirm what is the exact interval of convergence. Now what we mean by this is the following. Okay, so suppose this is my center and I find this at a distance r to be my interval of convergence. Now when we say exact interval of convergence, we mean the following. This interval could be like this, it could be like this, that means the endpoints are included. It could be like this, or for that matter it could be like this. So whenever you have an interval, there are 4 possibilities, so we have to figure out which one. In other words, we would have to test at the endpoints of the interval. So let's learn all these things with the examples. So the first one, we are only going to find the radius of convergence. So we are not going to go to step 2. So skip step 2 for now. So our power series is 3 times x to the power x minus 2 raised to the power k. and all of them always go from 0 to infinity, so we need not actually write this every time. Now we're going to find the radius and the interval both ways. One way will be the geometric series approach and also using the ratio test so that you get comfortable with it. So let's do the geometric series approach. So first thing, let's remember what geometric series was. Geometric series was a r to the power k is a geometric series, and it converges to a over 1 minus r, which is not important, but it converges if absolute value of r is less than 1. So the important thing is if absolute value of r is less than 1. Now let's look at this series that's given to us, and let's look at this. So see the similarity. So 3 is my a, and x minus 2 is my r. So in other words, r is same as x minus 2. And we know the convergence takes place when the absolute value of r is less than 1. So therefore, this power series converges if absolute value of x minus 2 is less than 1, because x minus 2 is same as this r here. Now once you have this, then you can write, this is from algebra, this means x minus 2 is between negative 1 and 1. Add 2 on both sides and you get x is between 1 and 3. So this is my interval of convergence. This is not exact, because remember, to find exact we have to decide what happens at the endpoints. That means what happens at 1 and what happens at 3, but we are not doing that in this particular question. Once I have my interval of convergence, the easy way is to just sort of graph it. So this is 1, and this is 3. So the center is obviously 2, and so the radius is 1. So the answer for this question is r is equal to 1. Now we are going to do the same question using the ratio test. Again, let me remind you, the ratio test was that you take limit k going to infinity, absolute value of ak plus 1 divided by ak. You find this limit and we called it L, and if this is less than 1, we have convergence. So for all these questions we are going to do the following. We'll do a step 1 would be find this guy, absolute value of ak plus 1 over ak. Step 2 would be we'll take limit k going to infinity. That will give me L, and I'm going to set L less than 1 to find the interval. So these are common sense step 1, 2, and 3. So let's do it. So first, ak plus 1 over ak. Remember absolute value. So what would I have? Remember, this is my ak. So I get 3 x minus 2 raised to the power k plus 1 divided by ak, which is 3x minus 2 raised to the power k. Now this is simple algebra. 3 and 3 cancels, and I'm going to be left with just x minus 2. Now I can write it once. This is x minus 2 raised to the power k times x minus 2 divided by x minus 2 raised to the power k. So this and this cancels, and I'm left with this. Now the next step is to take limit k going to infinity. So when I take k going to infinity, notice that there is no k here. There is no k. So when you take k to infinity, you are just going to have the same thing, absolute value of x minus 2. The next step is, so this is my L. So I'm supposed to set L less than 1 because that is when you have convergence. So when L is less than 1, so I say, okay, this must be less than 1 for convergence. So we are back to exactly the same result as we had here. So my interval is 1 to 3 because x minus 2 is between negative 1 and 1. So that means that x is between 1 and 3. So I have this as my interval. Center is 2, therefore radius is 1. So the answer is radius equals 1. So before we go to the next example, let's see that all that we have found till now matches up with our expectations. So we started with this series 3 times x minus 2 raised to the power k, k going from 0 to infinity. So see how similar it is to our general power series. So this is what a power series is supposed to be, and this is what we had. So clearly Ci were all 3. So Ci's were 3. Then A was 2. That means the center was 2. We can even write out some terms to get comfortable with this idea. So let's start from k equals 0. So I would get my first term to be just 3. Then the next one would be 3 times x minus 2. The next term would be 3 times x minus 2 squared. Then the next one would be 3 times x minus 2 cubed, and so on forever. So the question was, does it converge? And if it converges, for what values of x? So we found that it converges for x that lies between the interval 1 and 3. So this was our interval of convergence. And if you notice, 2 is the center of this interval, which is exactly what we should expect because 2 is the center of this power series. Okay, let's go on to the next example. So the next one was summation k going from 0 to infinity minus 1 raised to the power k x raised to the power k over 2 raised to the power k. Now first thing to notice is that this is going to be alternating. Okay, so we're going to do both ways. First we're going to do the geometric series approach. So for geometric series approach, we are going to see if can we make this series similar to our geometric series a r raised to the power k. So let's write this series in that way. So I have negative 1 raised to the power k, x to the k, 2 raised to the power k. So that should give you a hint that how can I make it look like this. So this is negative x over 2 raised to the power k, right? Because k is same exponent for all these three terms. So this is my power series and this is the geometric series. So what is the similarity? Clearly a is 1, not that we care for it, but the more important thing is r is negative x over 2. See, this r is same as this. Now the geometric series converges when absolute value of r is less than 1. Therefore this power series will converge when the absolute value of negative x over 2 is less than 1. So that means now when you're taking absolute value, negative has no value to it, so I'm left with this, which means absolute value of x is less than 2. So this means that x is between negative 2 and 2. So as our usual thing, let's draw the interval negative 2 to 2. Center is obviously 0 and radius is 2. So the best way to do it is after you find this, you should draw the interval and from there you can figure out the radius. So r is 2 and the center is 0. Now if you go back here to my original power series, you notice that it has x to the power k. So therefore a must be 0 because it's supposed to be x minus a raised to the power k. So the center is 0. That's why I have x to the power k. So it checks out. Okay, now let's do the same question using the ratio test. So in ratio test, the first step is to take absolute value of ak plus 1 over ak. So that means absolute value of negative 1 to the power k plus 1 x to the power k plus 1 over 2 raised to the power k plus 1 divided by ak, which is negative 1 to the power k x to the power k over 2 raised to the power k. Now we have done this kind of stuff in the previous chapter quite a bit, so you should be comfortable with it and we need not write in this cumbersome manner. So I would have negative 1, then x to the power k plus 1 over 2 raised to the power k plus 1 times 2 raised to the power k. Flip the denominator and this is what you would get. So this is minus now xk and x to the k plus 1, so that leaves me with an x. 2 raised to the power k and 2 raised to the power k plus 1 leaves me with a 2. So this is my step 1. Step 2 is take k going to infinity. Now so I'm supposed to take k going to infinity, but again there is no k here. You will see in further examples when k is there. but right now there's no k, so there's no difference, so I have this. We can drop the negative sign, and this must be 1, less than 1 for convergence. So again, this means absolute value of x is less than 2, which means you are between -2 and 2. Center is 0, radius is 2. So therefore r is 2, and the interval is -2 to 2. But again, we can't make this claim because we have to check the endpoints to be sure. And we are skipping that part in this particular question.